So to start us off, would you mind going through the Wallal expedition and why you're here in Perth?
I think everybody's heard of Albert Einstein, and his great prediction was that light is bent by gravity, to put it crudely. And this prediction was made way back in 1915. And the question was, how could it be tested? It's a tiny effect. And it was realized that during an eclipse of the sun, when the moon blots out the glare of the sun, the stars in the sky nearby can be seen even in the daytime. And that it would be possible with a careful measurement during a solar eclipse to see whether the positions of those stars in the sky had shifted. The shift is really, really tiny. This is a difficult thing to do. And at the time the prediction was first tested, which was 1919, it was right at the limit of technology. And the results of the 1919 eclipse were really not very good. It was carried out by a famous British astronomer, Arthur Eddington. It did serve to propel Einstein to international fame, however. He became a celebrity after Eddington's results were announced. But with hindsight, we see that it was a bit of a sort of fake story. And in 1922, there was an eclipse that passed over the Indian Ocean and into Australia, and a place called Wallal that I don't suppose anybody has ever heard of at the time. And an expedition was mounted from the University of Western Australia to go and observe this eclipse and get really careful measurements of the positions of the stars. Well, photographs, and the photographs were analysed, and sure enough, the stars had shifted in the sky. And now, of course, we're in no doubt about this, and we call this a space warp. That's the way I prefer to think of it. That the sun's gravity is a warping of space in its vicinity, and the light simply takes the straightest possible path through that warped space, which means to us it's just like having a gigantic lens in the middle of the solar system. And so that lensing effect is very small, but we now have examples of gravitational lenses which are huge, and you can see photographs of lensing by supermassive black holes and galaxies and so on that are very, very conspicuous. But that initial result back in 1922 was the first key step in testing Einstein's theory.
What was the importance of proving Einstein's theory?
A lot of people think that Einstein's theory, or they claim Einstein's theory, is the greatest human intellectual achievement. And it's more than just a theory of gravitation, space and time. It is that. It replaced Newton's theory of gravity, which had been around for 200 years, and is still good for most things. I mean, you don't use Einstein's theory to send a spacecraft to Mars, for example, but you do have to use it in a few circumstances with modern technology. For example, the global positioning system, without which we'd all get lost as we drive around Perth. That depends upon factoring in some subtle effects of gravitation on time. But mostly it doesn't have a practical value. But when I was a student, it was really a backwater of physics. It's called the general theory of relativity. And it was great to learn about because it's full of weird concepts like curved space-time and bending of light and slowing of clocks and things like that. Black holes hadn't been discovered, but that's happened soon after. And now it is really central to modern physics. So it went from being a backwater after many decades after Einstein to now being an absolutely critical part of our understanding of the fundamental nature of the universe. And so it's important not so much for a practical reason, but for people like me trying to understand how is the universe put together. It is one of the two pillars on which our modern understanding of physical reality is based, the other being quantum mechanics.
So would you say that there's a large societal influence that it's had on how we see the world?
I spent a career trying to communicate science to the wider public, and I think one of the things about physics that is fascinating, as opposed to biology, which is sort of easier subject, physics is full of abstract and weird concepts, things which seem to defy common sense. And so the general public loves to hear about things like black holes slowing time and wormholes and effects of curved space-time and so on. They love to hear that. Now, I find that in getting these ideas across to the public, it's actually a lot easier to teach Einstein's physics, that is the physics of space-time and gravitation and curved geometry, all these things, a lot easier than in the quantum realm. Quantum physics is a really very, very tough thing to get across.
Is that because it's just less reliant on common sense and sort of less intuitive to understand?
The way I would explain it is that in these days of virtual reality, it would be very easy to construct a world. And I'll give you one example. Einstein came up with a model of the whole universe back, I think, in 1917. And he had this notion that the universe might be finite, but without a boundary or an edge anywhere. And you think, well, how can that be so? If you go off into space, it must go on forever. And he said, no, it could be curved in a way that it wouldn't go on forever. It would join up with itself. And if that seems a bit baffling, well, people used to think the same about the Earth. They thought, well, either it goes on forever or there's an edge and you fall off it. But we know that's not true. It's round, but there's no barrier or boundary anywhere. You can go just around it and come back to where you started. So maybe space is like that. You can go off in any direction and keep going and come back to where you started. Now, it's hard to visualize. I mean, would feel, well, what would that look like? But you can imagine putting on a virtual reality headset and scaling things down. So the size of this universe might be, a kilometre or something, and you could walk around it and you could see, more or less the funny angles, and sure enough, you came back to where you started. And you begin to build up some intuition. So I think we're in with a good chance with things like curved space-time of getting the points across, particularly with good illustrations and, I think with things like virtual reality. But quantum mechanics is an order of magnitude more subtle and abstract, and it involves things like a particle can be in two places at once, and objects that have been close together and then go a long way apart still have some sort of telepathic link going on between them. And imagine the following. I throw a brick at a window, and there are two things that can happen. It can either bounce back at me or it can smash the window and go through. But imagine if I threw the brick at the window and it went through into the room but didn't smash the window. Well, that's the sort of thing that can happen at the atomic level in quantum physics. And that seems very counterintuitive, and people take a long time before, because they always want to say, well, what's really going on? And the uncertainty that is the hallmark of quantum physics is uncertainty and indeterminism, that an atom, you don't know what it's going to do from one moment to the next. And people always think, well, the atom must know what it's going to do, or the atom knows where it is or how it's moving. And our best understanding of quantum physics is even the atom doesn't have a well-defined position or motion, and it all depends on what we choose to observe. And so it's very subtle and still not totally agreed, even in the physics community, as to what we make of all that. How can we make sense of the quantum world? It involves many layers of subtlety, much harder to get that across to the public than general relativity.
Building on that idea of sort of what's really happening, would you say then that you're more supportive of an interpretation such as many worlds theory?
Yes, first I should explain. So when I say that there's uncertainty at the quantum level, what do I mean? Well, imagine you fire an electron at an atom, and it may bounce to the left or it may bounce to the right. And supposing you do it and it bounces to the left, well, you can do it under identical conditions, and next time it bounces to the right. And can you say in advance which way it's going to go? And you can't do that, but quantum mechanics enables you to calculate the betting odds. Maybe it's 60-40 or something, depending on the circumstances. But you can't know in advance what is going to happen. So one way of thinking about that is that there are two possible worlds. One is where the electron is going to the left, the other where the electron is scattered to the right. And that these two worlds start out completely identical, but after the collision, they differentiate, one into a left-moving electron, one into a right-moving electron. And if there's a physicist around doing this, the physicist will also have two copies, one in the left-handed electron world and the other in the right-handed electron world. So according to that point of view, there are two worlds which start out identical and then become differentiated. And by extension, there's an infinite number of such worlds. At any time anything happens at the subatomic level, which is all the time, there's a vast number of differentiating realities, and there's no single reality. And when I was a student, that idea was around, but you could find about 3 physicists who would speak for it. Now, the majority of theoretical physicists, at least those that I talk to over coffee, seem to subscribe to this many universes view. I used to be a fan of it because it seemed like it was a sort of rather neat way of getting around the problem of what is going on in the quantum world. But in recent years I've become more skeptical, and I now haven't got a fixed position as to what I think. But it's interesting that as a sociological phenomenon, that the physics community has gone from being very skeptical about this many universes idea to it being the party line. And I've seen this in a number of other things. For example, are there extraterrestrial beings out there? Gone from when I was a student, of course not, that's crazy science fiction. There's no life beyond Earth, to the universe is teeming with life and there's probably aliens out there somewhere. And these scientific fashions are fascinating in their own right to study, because our knowledge of the world, of both the quantum world and of the world of astrobiology, hasn't really changed that much in all those decades, but the fashion has changed.
Could you tell us a bit about what you're currently working on?
My interests are really very broad. So by profession, I'm a theoretical physicist, and mostly I've worked in cosmology and astrophysics. But I became interested about 30 years ago in what we would now call astrobiology, which is there life beyond Earth? How did life begin? And in particular, I'm interested in that transition from non-life to life. How did a mishmash of chemicals turn into even a rudimentary living thing? The short answer is we don't know. I take a particular point of view that tends to infuriate a lot of scientists, because there are a lot of them who are beavering away in labs trying to cook up life in a test tube, and they think, well, with a bigger budget they should be able to do it one day. And I think this is totally wrong-headed, because I think the origin of life is about the stuff of life, the hardware if you like, the molecular complexity, but it's also software, because the one thing that characterizes life is its information, not just replication. We all know about DNA replicating. It's not just information replication, but information management, the way that the chemical networks in any organism are coupled to information networks, and the information networks are controlling the chemical networks in a way that is very hard for us to understand. But even harder is, how did that come to exist in the first place? How can molecules write code? And I use the word code advisedly, because there is a universal genetic code that you and the birds and the plants and so on, identical way of converting the encrypted information in DNA into the actionable information in proteins. And that mathematical code, we don't know how it came into existence, or why coded molecular organization exists in the first place. How did that come about? I think we don't know. So that's something that I'm deeply interested in, and something I'm working on at the moment. I'm also involved in cancer research. You might think, how does that connect? It does in a way, because the origin of cancer is, so when you think about non-life to life was the first big transition, but then 2 billion years after that, there was another major transition, which was going from single-celled organisms to multicellular life. You and I are examples of that, and these plants and so on. It's multicellular life, and that's a very different way of doing life. The whole logic of life in multicellularity is different, and cancer is a breakdown of multicellular life and a reversion to like a single cellular precursor phase. And so all these things connect up, and I'm involved in all of them at any given time. So we've got the physics, cosmology and astrophysics still going on, origin of life and nature of biological complexity, and this cancer.
Correct me if I'm wrong, but you seem to think of life as sort of an information network controlling a sort of physical network of chemicals?
That's putting it very well.
Comparing that to something like artificial intelligence, or like a programmed software, which seems to be an information network controlling a sort of physical network of, or in this case, parts of a computer. Like, do you see there as being an overlap there, or potentially?
Yes. Yes, and you've hit on what is a perfect analogy. So supposing I say to you, a lot of people say, physicists, certainly I do, life seems like a miracle, you know, it's like magic. A magic puzzle box is the way it was expressed by Max Delbruck. Seems like magic, but a computer seems like magic to me. So when I look at something like Windows, and I think, well, this is amazing. We're so used to it that most people take it for granted, but it is amazing. Or if I say take Photoshop and think, well, how does that work? How do these shapes, you know, actually move around and get stored and so on? So supposing I go to a university and I say, I think Photoshop is like magic. Can you explain it to me? Now imagine if a computer scientist said, oh, absolutely, I can explain it to you, and took out a screwdriver, took off the back of the computer and said, well, in here we've got some silicon and there's some copper and there's some plastic and there's you know, a few other things, and we don't know the full details, but we're on the case, and it's got something to do with, if you look very carefully in the silicon, there's little patterns in there. It's got something to do with those patterns, and if we have a big enough budget, we'll be able to tell you and explain to you in terms of all this stuff in the computer, you know, what is going on. Well, we know that's baloney, because you go to a different room in a computer science department and you talk to a software engineer, and they'll talk you through the code and the operating system and the hierarchies and so on. And we know that to understand a computer, you have to know about the hardware, but you've got to know about the software. And that's true of life, but it's also true of AI. I mean, there is a dualism. And one of the things that scientists and philosophers can't really quite agree on is there a fundamental dualism in the universe as a whole, in the nature of reality? Can we explain everything in the universe in terms of one thing? Is there a theory of everything where we can boil down all possible concepts, structures and systems to a sort of base level of reality, bottom of a tower of turtles or something, at which you say everything ultimately is made out of that? Or is that in fact not possible, and that you need at least two things? Maybe you need matter stuff and mind stuff. I mean, that's an old idea which went out of fashion hundreds of years ago, but it's sort of coming back in a little way. And I'm skeptical that we can really explain everything just with a single concept. So from that point of view, I'm not a reductionist. Reductionism means we can boil everything down to, you know, one simple set of things. And I'm not convinced. I'm sitting on the fence on that one.
Do you think that a purely like physical theory of everything could be possible? The sort of a unification of physics as we see it now.
Right, it's certainly possible. It's a dream that's been around for quite some decades. The idea that we'll pull it all together and maybe there will be a simple mathematical formula you can wear on your T-shirt, and you go around with the, you know, this is the theory of everything. But even the most zealous believers that there is a theory of everything, and it might be string theory or something like that, even those believers would not claim that their theory would tell you how you were going to vote in the next election or why people fall in love or anything of that sort. It is not intended to be that. So I see science as really operating in two directions, down towards the sort of bottom level, and I don't decry that, because I think it's really important to identify those fundamental building blocks and the forces that act between them, and there you may have your formula. But then we go the other way, up through layer and layer of complexity, and we've been talking about life and living organisms. I don't think you will explain something about, you take some sort of biological phenomenon, you know, some sort of simple behavior of a fruit fly or something. You wouldn't explain that in terms of the superstring Lagrangian. Nobody would attempt to do that. But we need principles that apply at that level as well. So I don't think we'd be out of business if we had this formula on the T-shirt. I think there's still plenty to do going in the other direction. And a complete understanding of the universe requires both of those, both the reductionist and the emergent phenomena understanding. And whether we will ever have that total understanding is another question. You know, maybe we just had a dream run of 300-400 years of discovery, and we're going to run out of money or steam or something. I don't know. We're still going great guns at the moment. Anyway, there's this story that we like to tell in the physics community, that you don't really want to fund a project that lasts longer than the average PhD thesis. Because who's going to do their PhD on something that may not happen for another 50 years? But of course, a counterexample of that is the discovery of gravitational waves, which I never thought I'd see in my lifetime. And there's many a PhD student that's been through the system that might well have concluded, well, that was 3 or 4 years wasted, because that will never go anywhere. But sure enough, it did in the end. But there must come a time, if we hadn't discovered gravitational waves for 1,000 years, I think people will give up. And the same with the search for ET. Is there extraterrestrial intelligent life out there? We've been looking for 60, 70 years, something like that. If we look for 700 years and there's nothing, I think people would say, well, we'll find something else to do. So there is a point at which you will give up. But fortunately, we're living at this exciting time when there's a lot that's been found out, but still a lot to do. And we've picked a lot of the low-hanging fruit, but it seems to me that there's still an opportunity for young people to come into science, and particularly the interface between physical sciences and the life sciences. And nanotechnology and chemistry and information technology would all meet. There's still plenty of opportunity for new discoveries, not just of new phenomena, but new principles that can emerge in the coming decades.
And so speaking of discovering new phenomena and principles, do you think there's a tendency for experimentalists to find something and giving that to the theorists to understand, or theory sort of leading experimentation?
Well, the great thing about physics, because I'm a passionate physicist, is that this theory and experiment have always been more or less in step for some hundreds of years, and that's meant that ideas that come out of maybe just playing with mathematics have led to, well, let's do this experiment to test it. Gravitational waves, great example, but there are other things like the Higgs boson and antimatter and so on. All these things just were part of mathematical physics, which prompted investigation, experiment, and an observation, and led to discoveries. And sometimes something will be found, just comes out of left field. Well, what's that? And there was a good example when I was a young lecturer in London some decades ago. A new fundamental particle was discovered, and nobody knew what it was. And then the theorists raced around to try and figure out how it fitted in to some sort of scheme. And it didn't take long before it looked like maybe we understand what that particle is. But then the flip side of that is the Higgs boson, which was predicted in the 1960s. It took decades and decades. And you thought, well, is it really out there? But yeah, sure enough it is, and it was discovered. So it works both ways. And I think what we would all love is for that next unexpected experimental discovery. And maybe we'll get it. So now we have gravitational wave astronomy, a whole new window on the universe. Maybe somebody's going to see a waveform not like these ones that people are wearing on their t-shirts at the moment, because this is the signal you get from black hole binary encounters. Maybe it'll be one, it's got some really funny shape. You think, well, what's that? There's something out there we don't know about. And that would be really exciting. And the same thing in particle physics at the other end of the spectrum, the very small. Maybe the Large Hadron Collider, when they keep upgrading it, maybe in the next round of experiments there'll be a totally unexpected particle. I think they were hoping there will be, and that this will send us scurrying around and maybe developing a new theory. So this is all good. But we've been talking about the very large and the very small, the universe, particle physics. There's an awful lot in between where new discoveries could occur. And in particular, I come back to this interface of physics and biology, that the realm of large molecules or small organisms or something like that, where they overlap, and even simple organisms like bacteria do such clever things. They really do, to me, seem like magic. So the living cell is like this I mentioned earlier, Max Delbruck, a magic puzzle box. And it looks that way, and we should be prepared for surprises. We should be prepared to find that there's some new principles at work in those things. So this is an intermediate scale of size, but that's where we may very well find new science coming out of that.
I've heard you're involved with a new project called Nemo. Would you care to tell us a bit more about that?
Well, I'm involved only in the sense as I'm a well-wisher. Yes, I think the best way of understanding Nemo is this, that the prediction of gravitational waves, nobody knew at the time what the best sources of gravitational waves might be, but it became apparent a few decades ago that binary encounters, that is where you have two objects orbiting around each other, losing energy through gravitational radiation, and then colliding and coalescing, that this would be a prolific source. And in the early days, the prediction was that this would be mainly neutron stars. You'd have pairs of neutron stars locked in orbit, the orbit would decay and you get these events. But what's been discovered is that there seem to be rather more pairs of black holes doing this, which is a bit of a surprise. But the point is that black holes are really nothing. So what we've got is two blobs of nothing merging, and that's a very sort of simple setup. And indeed, the waveforms that you get from that, the gravitational waveforms, are all part of a pattern and fairly easy to understand. But now if you take two neutron stars are not blobs of nothing, they're blobs of stuff. And we don't actually fully understand what that stuff is. We know that there's neutrons, at least on the outside. The interior neutron stars, still something of a mystery. But now imagine that they're coming together and they're going to smash together and slosh around and probably collapse to form a black hole, and maybe stuff will come flying off. So you've got much more structure, much more complexity. But these neutron stars, I mean, it's an awesome encounter. You imagine this, because a neutron star is like an object with the mass of 1.5 suns squashed into the size of Perth. So these are incredibly dense objects, and the physics going on inside them and when they collide is going to be replicating, albeit fleetingly because of a fraction of a second, the conditions that prevailed in the early stages of the Big Bang. So it's almost like you're testing. It's a test bed for the physics of the origin of the universe. And so the gravitational waves emitted from those complex encounters could tell us a huge amount about the very early universe and about the nature of extreme states of matter. And NEMO is a proposal to dedicate a gravitational wave system to studying those particular encounters. And we know that they're there. We've seen at least one binary neutron star merger. And so they're out there, they're waiting for us to observe them, and all we need is the money to build the equipment to be able to study it in detail.
I was having a read of your book, What's Eating the Universe. You were talking about how, I think you were saying the vacuum may drop down in energy level and that could cause a sort of ripple effect. I was kind of curious if you could expand a bit on that.
This is a bit of a nightmare scenario. It's one in which the entire universe is destroyed. Not just, we've been talking about pretty awesome encounters of black holes merging and neutron stars merging, but I'm now talking about the entire observable universe being destroyed. And there are a number of different ways in which that can happen. But one of these, by analogy with an atom, so I think everybody knows that atoms can be what we call the ground state, but they can be excited. You can put energy into an atom, and when the atom de-excites, it emits a photon. And this is a well-worn territory in basic physics, atoms emitting light. Because the energy jump down from a higher energy level to a lower energy level. And the theory that explains all that is called quantum mechanics, and we have a lot of confidence in that theory. Well, you can apply quantum mechanics to everything, and in particular, we could imagine that the universe as a whole, a bit like a quantum system, might not be in its ground state, that is, its lowest energy state. And if it's in a slightly elevated, excited state, if something should trigger a transition down to that ground state, that would represent a huge transformation in the structure of space and time. You'd have a bubble that would expand out at almost the speed of light and destroy everything in its path. And that's one possible scenario for how the universe might end.
How do you feel we can inspire more young people into STEM fields and physics?
It was never an issue for me. I was passionate from the age of like 5. It was just a sort of wonderland. Today, young people seem to want, more direct stimulation. And it's true that we have to cater to that, and particularly with modern media. I think science is intrinsically fascinating, and so at a young age I think all children are fascinated by the world about them. So we need to get to them as young as possible, and there really is no, I've got grandchildren and they ask fascinating questions, even at the age of 3 and 4. And we just have to find ways of telling stories around their questions that can appeal to them and keep that alive. There's no problem, I think, say between the age of 5 and 12, to pluck an age out of midair. The difficulty, I think, is the teenage years, because there's so many distractions, so much competition, so many things competing for children's attention, that keeping them interested in science is a real challenge. The way science is taught in schools, I think, leaves a lot to be desired. There are some brilliant teachers who do inspire kids, but mostly their job is to follow a curriculum. You teach a bit of this, a bit of that, and so on. But there's one overarching thing when I think of my own school years that I would encourage in all children, and it infuriates teachers, which is, keep asking questions. Why is this? How can that be? Tell us about the other. And I became known, when I'm thinking now in my sort of mid-teens, known as irritating science teachers. The inevitable question from Davies, I once heard. Every time I learned something, I thought, well, what if you did this backwards? Or what if you put one of these with one of those? Or how can that possibly be? Because if you took that to an extreme, wouldn't it lead to something? And of course, mostly the teachers can't answer those things, but that's fine. I mean, if teachers say, well, that's a really good question, I don't know the answer, well, let's have a discussion of it. I think that type of open approach, there is too much notion that science is a worked out program, that we have an understanding of the world, and this is the question and this is the right answer, and you learn it, you take your exam and you go away. That's not the way science works. There's a lot of things we're confident in, but there's some things that are complicated or messy, or that it's a maybe answer. Those things should be discussed as well. I see science as about not what's right and wrong about the world, but unlocking the secrets of nature. It's fun, it's a community activity. I think it's especially important for girls. They like to feel part of a community. It's not an isolated male wearing a white coat in a soulless lab. It's a lot of people having a lot of fun together, and it's a community effort, and it's a terrific career path for young people of both sexes. And so I've been a strong advocate all my career, trying to get more girls into physics. Physics is particularly bad. Other subjects are not so bad, but physics suffers a lot from being underrepresented by females. We need to do more.
If you could find an answer to any big question today, what would that question be?
Well, it has to be the one that we talked about earlier, that are we alone in the universe? Or is there not just life out there, but intelligent life out there? So that's one that has been with me my entire career. That would be a transforming discovery if we woke up tomorrow and yes, we've finally discovered the presence of an extraterrestrial civilization. It would be fantastic.
If you were to give one piece of advice to a young aspiring scientist or someone looking to get into science, what would that piece of advice be?
Well, it sounds a bit boring, but it is don't forget your mathematics. So often in science, I have seen people being really interested in the ideas, but they've been limited in their professional competence because of a lack of mathematical talent. Mathematics, like languages, is one of these things that you get out of the way as early as possible. It's easier for young people to learn mathematics. So whether you go into physics or biology, or into engineering or accounting or investment, whatever it is, they're all mathematically based, and it's very easy to regard that the mathematics as a chore, as something that you have to learn alongside the science, but it's not. It's an integral part of our understanding of the universe. So you'll see me sitting here resplendent in this jacket with the logo of the Beyond Center for Fundamental Concepts in Science at Arizona State University, of which I am director. And so this is a center in which we wrestle with the great questions of existence, like the origin of the universe and the origin of life and time travel and space travel and the nature of consciousness and the destiny of mankind and so on. That's what we do. And it's a fantastic university, Arizona State University, that accommodates a center with such a vision. But it does, and I'm proud to be the director of it. I think it's a general answer that in this day and age, no research university worth its salt is going to be isolated from the community, the broader community, and that's got to mean international. I mean, these days, big science is international, and we take things like particle physics and astronomy, cosmology, the network of researchers, theory and experiment. It's a global enterprise, and so it's an essential part of the job. In fact, you might think, well, why am I here in Australia? Shouldn't I be sitting at my desk at Arizona State University? They've let me out. You know, are they anxious that I should get back quickly? Quite the opposite. It's expected that we go around the world and I wave the flag for our wonderful university and for the research that we're doing there, and connect with other scientists and form collaborations in many countries. And that's the way it works. Increasingly, science doesn't belong to one country or one institution. It's a community effort.
Paul is a physicist, cosmologist, astrobiologist, and a best-selling writer. He's the Regents Professor and Director of the Beyond Center for Fundamental Concepts in Science at Arizona State University. His research focuses on the deep questions of existence, from the origin of the universe to the origin of life, the nature of time, quantum reality, the search for intelligent life in the universe, and the deep evolutionary roots of cancer. His work on quantum processes in the Big Bang is widely cited as the explanation for the large-scale structure of the universe. He's the author of over 30 books, and the most recent of which is What's Eating the Universe and Other Cosmic Questions.